My second lecture. This lecture I'm going to talk the kinds of liquid crystal laser, particularly the distributed feedback laser. I have already told you what this laser, but I also introduce defect mode lasers. There are three kinds, which has the phase jump as a defect, and the insertion of isotropic or anisotropic defect layers gives a different type of defect mode lasers. And I just very briefly introduce DBR, distributed Bragg deflector lasers. It's a kind of fabric-perro cavity mode lasers, and some combination of DBR and DFB are also possible to decrease the threshold. So maybe I can talk this, and if I have time, I will talk also things. Okay, before telling my story to you, first I will introduce our samples, because sample preparation is a very crucial issue. To introduce defect, fluid liquid cannot be used. We use this type of main chain polymeric liquid crystal for the bulk. So we use the aromatic polyester containing the following three units. So it is a main chain polymeric liquid crystal. It's a thermotropic liquid crystal. So without any solvent, this aromatic polyester forms a liquid crystalline phase. So we use two kinds of this polyester. One has the chiral unit, 20% chiral unit, and the other one has no chiral unit. So by changing the mixing ratio of sample A and sample B, we can tune the helical pitch. So the fabrication can be made like this. We dissolve this sample A and B in 10% chloroform solution, and then spin coating on the substrate covered with rub polyimide. This is the same as the treatment in normal liquid crystal. And then during the evaporation of chloroform, the material forms a liquid crystalline phase, so that the beautiful helical structure can be formed by these procedures. So for the thickness, we can tune the thickness by changing the speed of spin quarter, and we can make 2 micron to 1 micron thick classic liquid crystal film. And for the pitch, as I said, by changing the ratio of sample A and B, we can tune the helical pitch like this. So if we use the higher the chiral content, we have blue reflection band, and we can also have green reflection or red reflections. And we can also tune the helical pitch very precisely. So So this is the sample we used, and this is the same as I showed before. We can make a distributed feedback laser by this way. And this is one of the example of the lasing like this. So what is important is how can we make the stable laser emission with low threshold. So for that purpose, first I want to show density of state. I will tell you the density of state later. And this is the reflection spectrum of classic liquid crystal. This is a simulation for right-handed circularly polarized light. There is no reflection. This is transmittance, sorry. So 100% transmittance. And for left-handed circularly polarized light, we have a photonic gap like this. And if we calculate density of state, at the edge of this photonic gap, we have the maximum density of state. So at this point, we can have lasing. Okay, so to achieve lasing action, of course, we need to have the large emission rate, like this. Emission rate is given by this film golden loop. This is the electric field of mode 1, and this is the transition dipole. So this is the inner product of electric field and transition dipole. So if the electric field is parallel to the transition dipole, of course the emission rate becomes larger. And also the important factor is the density of state. So we multiply by the density of state, so we have to have a higher density of state, and which is given by this equation, as I told you before. So to have a large emission rate, sorry, this is EI, sorry. The electric field and the dipole moment are parallel to each other, and M, this density of state must be large. So we have to have such kind of condition. So for that purpose, I will introduce the comparison of the Dfb lasers using this dye and this dye. This is commercially available dye molecule, and this is the gift from the Tim Swager in MIT. This dye have advantage that the dipole moment along this direction is well aligned to liquid crystal dielector because of this trypsin group, the liquid crystal molecule. These trypsin group suppress the fluctuation of liquid crystal, so that if we dope the classic liquid crystal with this molecule, dye molecule, the order parameter increases. Normally, of course, the order parameter decreases if we dope a different type of molecule. But in this case, we can increase the order parameter. So we want to compare how the orientation of dipole moments are important for lasing by this example. So this is the experimental, the spectrum and simulation spectrum. in DCM and P2PV, alphanilambinium. And you see the selective refraction gap here for left-handed circularly polarized light, and here. And you also see here for DCM too. And the experiment and simulation agrees quite well. And this is the experimental results. The red one is reflection, and blue one is emission, and this black one is lasing emissions. So when the exciting light is low, the power of the excitation is low, then we have this kind of emission. Of course, emission has the dip due to the reflection band, and with increasing the excitation power, we finally have lasing emission like this. This is the case of PPPV, and this is for DCM. Interesting thing, in these two cases, we slightly change the photonic band gap, so that in this case, photonic band gap, the lower energy edge of photonic band gap is located almost at the top of the emission, maximum of the emission. And then the lasing occurs here. And this is also the same. However, if we make the crystallic liquid crystal, which has the longer pitch, so in this case, almost this higher energy edge is located near the emission peak in both cases, but still lasing occurs at the low energy edge. So so lasing always occurs at the lower energy side of the photonic band. So the question is why? So this is how the two dyes align to liquid crystal. And in case of P2V, with increasing the dye concentration, the order parameter increases. So it's well aligned. This is from the absorption anomaly. This is from the emission anomaly. And in DCM, with increasing the content of dye, then order parameter decreases. So this molecule, this dye molecule, well aligns to liquid crystal dielectric. And so I want to. So as I said, this part and this part is important. And this is the orientation of the electric field direction and the dipole. And this is the density of state. So we can understand why lasing occurs at the edge of the reflection bands. That is because this is larger. However, still we have to answer why the lasing occurs at the lower energy edge. So the question answer is related to the optical eigenmode of classic liquid crystal. This is the optical eigenmodes of crystallic liquid crystal. Actually, the eigenmodes of crystallic liquid crystal is the elliptically polarized light, not exactly the circularly polarized light. And moreover, the polarization, ellipticity changes with wavelengths. So it is very complicated. As you know, if you have the polymer, stretched polymer, so it's a uniaxial. In this case, the two eigenmodes is linearly polarized light of stretched direction and perpendicular direction, and it doesn't change with wavelengths. However, in case of crystallic liquid crystal, eigenmodes changes. If we consider right-handed crystallic liquid crystal, one of the eigenmode is left circularly, left elliptically polarized light. This is this one. Okay. This is the inverse of wavelengths, and this blue region is photonic band. Okay, and this ordinate corresponds to the ellipticity. So the ratio of two x component and one y component of the electric field. So here Ex and Ey equal 1. That means a circularly polarized light. And here correspond to linearly polarized light, and which is parallel to director and perpendicular to director. So if you look at the other eigenmodes is more or less right elliptically polarized light. However, optical eigenmodes changes drastically in the vicinity of photonic band depth, and in the lower band edge, the optical eigenmode is parallel to director, but this side, higher energy side, the polarization is perpendicular to director. So that is a very important difference. So the situation is like this. Okay, first let's consider this term, electric field times the dipole moment. And since the order parameter of polymer dye that is larger compared to DCM commercial dye, so that in this case at the lower energy edge, the dipole and electric field are almost parallel to each other. So this value becomes largest here. However, at the edge of the higher energy edge, the dipole and electric field eigenmodes are perpendicular to each other. So this gives a minimum. And this difference is larger if the system has higher order parameters. So molecules, if molecule is perfectly aligned, then this must be much, much larger. So important to have large, this value is that the dye, the transition moment of dye well aligned to the liquid crystal molecule. So that in that case we have large value. And then the other important factor is the this density of state. as I said, that the density of state becomes maximum at the lower and higher energy edge. So by multiplying the density of state and this figure, we have this kind of situation. So emission rate is given by this kind of figure. So any time, if transition dipole is parallel to the liquid crystal local director, the maximum emission rate appears at the lower energy edge, longer wavelength edge. So always we have the lasing at this edge. So that is the reason. So this is a kind of summary in this part. So density of state is given by this one. So transition dipole is parallel to local director. Then the transition dipole emission is parallel to the optical modes for lasing. Then most efficient use of emission is possible, and lasing occurs at this position, not this position. So the one of the issue to have good dye is dye must be very resistant to the strong light and chemically, but at the same time, if dye well aligned to molecule, that is much better for lasing. Okay, so these are the first part, and the next part is defect mode lasing. Okay, as I briefly told you, there are several kinds of defect. One of the defect is given by this kind of phase jump. See, here is the continuous the helical structure, but the phase changes by 90 degrees here. Sudden change of phase is introduced between these two helical structures. This is one of the structure of defect modes, and the other one is the insertion of different layer. We can introduce the isotropic layer such as polymer film, and also we can introduce a pneumatic liquid crystal here. It's a uniaxial medium between these. So I will introduce all of these defect mode lasing. This is the theoretical paper which shows the defect mode. It's 1999. The Yang et al. Introduced the isotropic layers as a defect, and by changing here, these are refractive index and pitch and so forth. Anyway, so this is the position of defect level, defect mode state. By changing the refractive index of defect layer, or by changing the thickness of defect layer, defect position changes like this. Actually, this level and this level correspond to the lower and higher energy edge of the photonic band. So photonic band is here. So defect level moves within in the photonic band with refractive index of defect layers. And this is the simulation. Almost in the middle, you have this kind of defect level, very sharp defect structure here. For left or right circularly polarized light, you have the diffraction peak or transmission minimum. So when the thickness of defect layer becomes thicker, the mode position changes become steeper. And so this becomes more and more. And defect mode is located in the middle of bandgap when the phase sweep of pi over 2. So if the defect layer is quarter wave, then the defect position is in the middle of the photonic bandgap. This is the situation. And the Schmidtke also calculated many types of defect, which is the combined defect of phase jump and twist defect. So he used this kind of phase jump and also the insertion of another layer. And in this case, in addition to the another layer, phase jump also occurs. So this is the result with, for instance, with increasing phase jump, the defect state changes like this. And so these are the result with increasing defect thickness. By changing the defect thickness, this one, the thickness, for instance, if we focus on 90 degrees phase jump, this position changes and appear from the other side. So this kind of change occurs. So in this way, we can tune the defect position. This is another trial to make defect structure. This is again from Ozaki's group. They use the Gaussian, the light, then the heat this part. And as I said, the pitch of caustic liquid crystal is very sensitive to the temperature. So some caustic liquid crystal shows the positive temperature dependence, and some of them gives a negative temperature dependence. So pitch changes with temperature, becomes longer or shorter by increasing temperature. So in both cases, we have defect with different pitches here. So that is the effect. And the other authors, Schmidtke et al. And also Ozaki et al. Actually shows the defect mode lasing by experiment. So he introduced 90 degrees defect, and this is the intensity profile as a function of pump energy. So in case of defect mode lasing, the lasing threshold is around here, but if we look at the edge mode lasing, threshold is here. So the threshold of defect mode lasing is much, much lower compared to the edge mode lasing. So this is because the density of modes of defect level is much, much higher than the band edge. So this is very attractive data. Then we also made the isotopic defect layer insert the isotopic defect layers. We use a polymeric liquid crystal, as I mentioned, and we insert the polymer layer. Actually, we use PVA, and we made this kind of structure: crustic and isotopic polymer film and crustic. And then we can observe defect here. Then this is still simulation. This is the simulation of density of state. So density of state shows a very huge peak compared to the edge mode. So the defect mode lasing is advantageous compared to the edge mode lasing. And this is an experiment. Actually, we observe the edge, density defect mode lasing at this pumping power. But for the lasing at the edge, we need more power to laze. And actually, in this case, this is the actual film. So since we use only a polymer, so we can peel from the substrate. So just a very thin film, like 10 micrometer. And so it's 5.5 micrometer thick lasers. So we can freestanding film for laser. Okay. Oh, okay. So another beetle story I want to tell you. This, as I said, every beetle has left-handed helical structure. So we have this kind of reflection. This is selective reflection. But there are different type of beetle which has reflection for left-handed and right-handed, both. So these are the name are different. These guys are different, okay? And how they can reflect both left and right-handed light? You can guess how they do. It's very simple. They just insert a halfway plate. If we observe the cross section of the skin, actually we can observe the helical structure and halfway plate nematic. So this is the uniaxial halfway plate nematic, and the left-handed helix. So in this case, if we input a left-handed circularly polarized light, this is reflected back from the left-handed classic liquid crystal immediately. However, in this case, right-handed circularly polarized light can pass through the first classic layer. However, because of the halfway plate, right-handed light changes to left. So this left-handed circularly polarized light is reflected back. And then left again changes to R. Then R can propagate through this classic layer. So R is also reflected back. In this way, this beetle, they reflect all kinds of light. So the reason why I introduce you is we made this kind of structure by using the classic liquid crystal and nematic liquid crystal. So this way. So here is a classic liquid crystal, and we insert a nematic liquid crystal with dye and classic liquid crystal. So we can, so this nematic layer acts as a defect. And we also use the same dye, and then result is like this. So here is the defect, and we can lace at the defect, and in some case we can lace at both at the defect level and also the edge level. So, but at least this defect lacing is more advantageous in view of the threshold field power. Okay. So this is the so these are the story of defect mode lacing, and the next one is DBR lacing. DBR is distributed black reflector lacing. And if you consider the difference is only the thickness. Normally, the defect mode lacing, we use the thin defect layer, like quarter of wavelengths. But in this case, if we use a very thick insertion, this isotopic layer or nematic layer is sandwiched by the crystallic liquid crystal. These are the black reflector. So we have black reflection. And in this case, it's very simple. It's a Fabry-Pellot cavity modes can be observed. But in this case, since the nematic is the anisotropic medium, so depending on the thickness of the nematic layer, the phase changes. So, for instance, if the thickness is n lambda plate, corresponding to n lambda plate, then the right-handed circularly polarized light also the right-handed circularly polarized light by passing through the nematic layer. So this go out. However, if the thickness corresponds to n plus half wavelength plate, then the left-handed circularly polarized light changes to R, so it is reflected back. So this is reflected. But in this case, if we emit light inside, then the right-handed circularly polarized emission is confined in this range. So we can lace here. So this is the story. In this case, reflection bands is from this reflection band. But in this case, in addition to this reflection bands, we have to consider the nematic layer. So reflection is modulated like this. So at the minimum reflectance, we have the situation that lacing occurs. This is actually the experimental results. To confirm this, we use a wideband reflector using the blue, green, red crystallic liquid crystal, and the nematic liquid dye containing nematic liquid crystal was sandwiched by a broadband crystallic liquid crystal like this. Then the modulation by the nematic occurs like this, and at this transmittance maximum, region maximum, the lacing occurs like this. And the nice thing about using nematic liquid crystal is by applying the field, nematic liquid crystal change the orientation so that we can change the effective thickness of the defect layer. So, for instance, in this case, lasing position changes by applying an electric field. So this is because of the change of the orientation of nanomaterial liquid crystal. So I think that it's almost time, so I will stop here. I have something that this is not so important, so I stop here. Thank you very much.
Questions, please? Yes?
I have a question about the material. So why do you use the polymeric liquid crystal instead of the low molecular weight, molecular or polymer network, or polymer sports liquid crystal?
Okay, we can also use photopolymerizable liquid crystal. We can also use, but I will tell you the very well controllability of this material. But this is very easy to handle, and we can control the pitch and thickness